Okay, cool. So continuing on from this morning, actually related to some of the questions this morning, what I want to do in the second lecture today is kind of go down to a finer spatial scale and try to think a little bit about the determinants of distribution economic activity within cities. In particular, I wanted to speak about a paper that used the Berlin Wall as a natural experiment to try to provide evidence that these quantitative models actually have explanatory power in terms of being able to predict what's going on in the data. Because, of course, one challenge, as we discussed in the first lecture, is in these models, I can typically match the cross-sectional distribution of activity completely in the initial equilibrium of the data by allowing for differences in productivity and housing supply and so on. And so obviously, then I have as many degrees of freedom as observations, and so there's no explanatory success in the fact that the model is able to explain the cross-section, because by construction it's set up to be able to explain the cross-section. And so what I would like to know is, can the model do a successful job explaining the impact of shocks, right? If I observe a shock in the data and I start from that initial equilibrium, I do a counterfactual, how successful is the model in predicting what happens following that shock? And so that was one of the sort of challenges that we tried to take on in this paper. And it's a joint paper with Gabriel Alfeld, Daniel Sturm, and Nicholas Wolff. So what's our motivation? Well, it's very closely related to what we talked about in the first lecture, that economic activity is unevenly distributed across space. But that's true not just about cities as a whole or economic activity at the regional level, which was the focus in the previous lecture. It's also true, perhaps even more so, at the disaggregated level within cities, across city blocks. So, for example, advertising agencies in New York are disproportionately concentrated in Midtown Manhattan. Financial services in London historically were concentrated within the square mile of the old Roman city. And so even particular economic functions within cities are highly concentrated. And so obviously a key research objective is determining the strength of agglomeration and dispersion forces that underlie these concentrations in economic activity. And so the agglomeration force will typically be some form of increasing returns, again connecting with the first lecture today. The dispersion force will be scarcity of land, as in the earlier lecture. And then, of course, within cities, as you concentrate more people in the city and expand its geographical boundaries, an additional dispersion force is that commuting becomes costly. It takes longer for people to get to work each day, and that's obviously costly in terms of real resources and in terms of people's time. So working out how strong these forces are is critical to a lot of public policy issues. So in particular, the productivity advantages of cities depend crucially on the strength of agglomeration forces. If I think about constructing transport infrastructure, the impact of that on the spatial distribution of activity will depend critically on the extent to which there are agglomeration forces. So as I move things around the city with a new transport link, how will that change productivity and amenities in different parts of the city? And obviously it's crucial, as we were discussing in the first lecture, to questions about optimal policy, such as local taxation and regional policy, place-based policy. And so what we're going to try to do in this paper is firstly develop a model for thinking about economic activity within cities. And then secondly, we'll actually try to structurally estimate the parameters of that model. So to actually work out how strong these agglomeration forces are, and then look for our estimated parameters. Can the model do a good job predicting the impact of these real world shocks, such as the division of Berlin by the Berlin Wall and its reunification following the fall of the Iron Curtain? So what's the challenge doing this? Well, the challenge is very closely related to what I discussed in the first lecture. So did you have a question?
Yes, about the dispersion forces you mentioned. Given the examples you made, Madison Avenue, the city of London, shouldn't we think about congestion as being a dispersion force that drives these places, because these are very bad places to live in as a person?
Yeah, absolutely. So congestion could be another one to add to these two dispersion forces here. In the model I developed today, I won't directly have congestion. So there'll be travel times within the city, and we'll calculate them based on the transport network. So underground railway lines, overground railway lines, buses, trams, and so on. But we won't allow those travel times to be a function of the number of people traveling on a route. And so the model I developed today won't perfectly capture that force of congestion. But it is possible to do so, in particular if congestion on a route is a power function of the number of people flowing on that route. It doesn't actually change things very much. It just adjusts the parameters that you need to, the interpretation of the parameters when you estimate them from the model. So I have a paper with Esteban Rossi Hansberg and Fernando Monte in the AER when we kind of make that point in the appendix to the paper. And then more substantively, if you want to model congestion in a way that does make a difference, Kostas Sakalakis and Trev Allen have a paper coming out in the economic studies where they do model congestion as a dispersion force. And what I do today will have land scarcity and commuting costs, but we won't have congestion. But you're absolutely right, that could be another force for dispersion. So as I was saying, the challenge here is going to be very closely related to the challenge in the first lecture. We want to know how strong agglomeration forces are, but there's this competing explanation, which is why are things concentrated? It's not agglomeration. It could instead be variation in natural advantages, first nature geography. So we need to distinguish second nature geography from first nature geography within cities. And so, for example, I might see really high land prices in a particular neighborhood in New York, say Chelsea, very, very high land prices. Are those land prices high because there's some agglomeration benefit of people living there and it being a concentration of high residential activity? Or is it just because Chelsea is a really nice place to live? It's close to the river, there are a lot of other amenities that make that place an attractive location to live. We want to try to separate those two things out. Historically, one way of doing that has been to try to regress measures of productivity or amenities or wages on measures of the density of economic activity. So regress, say, productivity on employment per square mile and try to find if there's a correlation between productivity or amenities and the density of economic activity. Clearly, that's problematic for a number of reasons, because obviously productivity affects density. The reason a place might have a lot of people living there is precisely that it's a productive place to be, or it has high amenities. And so reverse causality is a challenge. There can be omitted variables that affect both productivity and density simultaneously. So people have tried to find instruments. And so again, this is still an area for exciting further research. It's difficult to think of variables that only affect productivity or amenities through density. Perhaps the best approach is to use a geological substructure. So there's a very nice paper by Rosenthal and Strange, where they make the point that it's easier to build skyscrapers over bedrock. And so you use the underlying geology as an instrument for density. And that's an instrument which you think might satisfy the exclusion restriction. And there's no reason why the rocks underground should directly affect economic activity if you're not drilling for oil, other than through allowing you to build high density buildings. So we're going to try to find a new approach to separating out agglomeration forces from these natural advantages. And we're going to use natural experiments of the division of Berlin by the Berlin Wall. And more generally, we're going to use that experiment to say something about the spatial scale over which these agglomeration forces operate. How localized are they within cities? Do they extend for kilometers within the city, or are they concentrated on a very fine spatial scale of individual city blocks? And so the way we're going to do it is use the division of Berlin as an exogenous source of variation in the surrounding concentration of economic activity. So in particular, we're going to develop a quantitative model of spatial structure within the city, which allows for agglomeration and dispersion forces, while also allowing for first nature geography, variation in natural advantages. And in our case, there's going to be three sets of natural advantages. We're going to have what we call production location fundamentals. So those are things like access to natural water, access to a deep harbor, sort of features of first nature geography that make a place an attractive place for production, independently of surrounding concentration of economic activity. We're also going to allow for residential fundamentals. Living next to Central Park may be pleasant, purely because you're next to Central Park, rather than the number of people living around you. We may have scenic views, leafy streets, maybe these sort of things that don't directly depend on the density of economic activity that make a place an attractive place to be. And then we'll also allow for variation in the transport network within cities, because obviously, a key feature of real world cities is, whether you're living near a subway stop or near a rail station really affects the local house price because of the ability to commute quickly to work. And what I do today, we're going to take the transport network as being exogenous, but as Eric asked at the end of the last lecture, we might think that the transport network itself is endogenous to economic activity, and we'll discuss some recent approaches where people have been trying to endogenize it. But in what I do today, I'll take it as given, which I think is sort of well described by the Berlin experiment. When the Berlin Wall was constructed, subway lines were sort of often blocked off at the boundaries, or they ran through East Berlin, through stations with armed guards, stopping everybody getting off the subway line. And so we'll take account of those changes in the transport network, but we'll take them as being exogenous, which we think is a fairly good description of the Berlin experiment. There's very little new building of railway lines in West Berlin, a tiny bit, very little. So with the model to think about agglomeration dispersion forces within cities, allowing for that first nature geography, And then we'll show how we can structurally estimate the model. What's the data we're going to need? Well, we're going to need land prices. They're going to summarize how attractive it is to be in a particular location. We'll see that through the model. As a location has higher productivity or amenities, it becomes a more attractive place to live or produce, and so land prices rise. But if we want to separate out agglomeration forces in production from those in residential decisions, we'll also need to see employment by workplace separately from employment by residence. And so these are going to be the three key sets of data that we'll need to structurally estimate the model and separately distinguish agglomeration forces in production and residence. And then we'll combine that with this exogenous shock to the surrounding concentration of economic activity. Yep.
You mean workplace location, relevant location?
Yeah, so I should have defined that more clearly. So yeah, what do I mean by this? Employment by workplace means the number of people in a city block that work there, regardless of where they live. And then employment by residence is the number of people who live in a city block, regardless of where they work. And so, for the city as a whole, there's going to be a commuting market clearing condition that the sum of this variable is equal to the sum of that variable, right? That the number of people employed in the city is equal to the total number of people commuting to employment somewhere within that city. Does that make sense? Yeah. So it's number of people working in a block, there's workplace employment regardless of where they live. Residence employment is the number of people living in a block regardless of where they work.
So is there like commuting from outside the city?
So great question. So one of the things that's useful about our application to Berlin is that in 1920, the Germans defined what they called Gross Berlin or Greater Berlin. And they defined it very, very generously. So it included sort of large surrounding bits of open space and lakes and woodland and so on. And so when we look at the data for Berlin, there is a very small amount of commuting from outside that definition of Greater Berlin, but it's trivial. It's a few tens of thousands of people for a city that's around 4 million people in total. And so we're going to, and in particular during division, West Berlin was a completely closed island where you could travel from West Berlin to West Germany, but you couldn't travel from West Berlin to East Berlin without permission, or travel from West Berlin to the surrounding East German countryside. And then again in 2006, at least at that time, there wasn't that much commuting from beyond Greater Berlin. In the years since then, it's increased in magnitude. But when we look in the data, we actually check how the difference between workplace employment and residence employment, and it's pretty small, just a feature of our application. But in general, in other applications, if you have a lot of commuting from outside the city boundaries, you're going to need to take that into account. Okay. So I think was another question? Great. Okay, so in terms of the structure of the talk, I'll say a little bit about the historical background, why this is a useful natural experiment to try to structurally estimate the model, then go through the structure of the model, tell you a little bit about our data, show you in a reduced form way what happened in the data, then structurally estimate the parameters and show that actually it does a really good job in terms of approximating what we see happening in the reduced form moments in the data. Okay, so the division of Berlin actually dates back to a protocol signed during the Second World War for the sort of between the Americans, the British, and the Soviets, looking ahead towards the sort of future organization of the occupation of a defeated Germany. And so the Americans, British, and Soviets initially organized Germany into what they called occupation zones. And so the Russians and Soviets would be in the east because they're advancing from the east. And the Americans and the British would be in the west because their armies would be advancing from the west. And then later on, a French zone was created out of the British zone. And then Berlin as the pre-war capital of Germany, even though it was east of the western boundary of the Soviet zone, so it was deep inside the occupation zone of the Soviets in Germany, it was agreed that as the former pre-war capital, Berlin itself would be split up into occupation sectors. But again, the Soviets in the east, the Americans and British in the west, and later on a French zone was created out of part of the British zone within Berlin. And originally the idea was not for the city to be divided. Originally the idea would be, these occupation zones were just sort of practical measures. You didn't want troops from different forces living next to one another for fear of accidental conflict breaking out. And it was just thought to be pragmatic to have different occupation sectors. But there would be a commandatura for the city as a whole that would jointly administer the city, on which the Americans, the British, and the Soviets, and later on the French, would all be represented. And so how were the boundaries between these occupation sectors decided? Well, it was decided to follow pre-war district boundaries in Berlin. So these were things like the suburbs of Berlin. those of you who've been to Berlin, Mitte, Kreuzberg, the different areas of the city. So in London, that might be Hampstead and Chelsea. New York, it might be the Upper West Side, the Upper East Side. So these are different neighborhoods of the city that didn't really have any large administrative meaning before the war, but they just decided to respect the boundaries between those pre-war administrative divisions. And as I said, the idea was we keep them with the same east-west orientation as the advancing armies. And the boundaries between the sectors were chosen to give roughly equal pre-war population to the Soviets, the British, and the Americans before the French zone was created out of part of the British zone. And then although the idea was initially to jointly administer the city, with the onset of the Cold War, East and West Germany are founded as separate states, and separate city governments emerge in East and West Berlin in 1949. And then from that point onwards, the adoption of Soviet-style policies of command and control in East Berlin rapidly concerns any form of economic interaction between West and East Berlin. As you all know, for a while, it remained possible to travel from East Berlin to West Berlin until, to stem the flow of refugees leaving East Germany for the West, the East German authorities in 1961 construct the Berlin Wall. And then from that point onwards, there's no local economic interaction between either side of East and West Berlin. What's nice about this experiment from our purposes is that before the Second World War, no one was sort of anticipating that Berlin would be divided in this way. If you go back to the early 1930s and the late 1920s, there was no idea that the city would be divided in this way. And the boundaries between these occupation sectors was driven by these exogenous geopolitical concerns, was not in any way influenced by the characteristics of individual city blocks within Berlin. So what did the division of the city look like? Well, here in these dark blue polygons, these are the pre-war districts of Greater Berlin. The green lines are the pre-war suburban railway and underground railway lines. The gray lines are the city blocks on which we have data. We have around 15,000 city blocks in the raw data. And then this red line here is the inner segment of the Berlin Wall, which ran through the heart of the city. And actually cut off West Berlin from the pre-war central business district. So this area here is the district of Mitte, that was the pre-war central business district. And so following the division of Berlin, West Berlin loses access to its pre-war central business district. And then it also loses access to East Germany because there's also a part of the Berlin Wall that goes all the way around the outside of West Berlin. And so we want to try to develop a theoretical framework to think about the impact of the division of the city. And so how are we going to do that? Well, we're going to build on the sort of canonical urban model of the internal structure of cities, Lucas and Matthew Hansberg, 2002. And so, paralleling what I said earlier about the economic geography literature between regions, the traditional theoretical literature on cities had developed very kind of stylized models of cities. So the classic model going back to the 60s is the so-called Alonso Muth-Mills model. What was that model of the city? Well, the assumption was all employment is in the center of the city, in the central business district. People face commuting costs in traveling to work there in the central business district. Where are the most attractive places to live in the city? Well, those are obviously those closest to the central business district, so they'll have high land prices. And then further away from the central business district, land prices will be lower, exactly to compensate people for the higher commuting costs. And so you have a rent gradient within the city, it's monocentric, the highest land prices in the center, and then land prices decline monotonically with your distance from the center of the city. And originally there's a very stylized geography, so the city is a one-dimensional straight line. Okay. And then a kind of key theoretical contribution in Lucas and Rossi Hansberg was to sort of generalize that model in two key respects. Firstly, to go from a one-dimensional line to two-dimensional space. So here the city's a circle rather than a line, so latitude and longitude. And then secondly, to allow for non-monocentricity. That you don't assume all employment is concentrated in the central business district. You allow for endogenous allocations of land between commercial and residential use. And so Lucas and Rossi Hansberg show that in general, you can create non-monocentric patterns of economic activity even when the city is a symmetric circle. Why is that? Well, if you have an agglomeration force, such as knowledge spillovers, that's a force for concentrating all employment in the central business district. But of course, that's very costly in terms of commuting costs, because everybody has to travel to work in the center. And the reason why you might want to have a non-monocentric pattern, where you have, say, commercial employment in part of the radius emanating from the center, and then a residential belt, then another commercial belt, then a residential belt, then a commercial belt, and so on, is that saves on commuting costs. And so when commuting costs are sufficiently high, agglomeration force is sufficiently weak, you can support this pattern of non-monocentric economic activity within the city. However, if I think about taking that model to the data, it's sort of challenging in a couple of respects. What are those two respects? Well, obviously, when I look at a real world city, such as Berlin, it's not a perfectly symmetric circle. You have, differences in transport network across different blocks within the city. You have some forests and lakes in different parts of the city that people may value and have access to. Other parts of the city may have no forests and lakes. You may have running water in canals and rivers in the center of the city, but not in other parts of the city. And so it's very difficult to know how would the properties of the model change once we allow for all of that asymmetry. And so again, we'd like a model which could build in that richness, but we'd still be able to say something analytically about the properties of the model and characterize its properties. The other thing that's would be very hard taking one of these traditional models to the data is in this sort of traditional theoretical literature on non-monocentricity, workers are all identical. And so if I think about a worker's commuting decision, there's a sort of indifference condition. If I decide where to live, I look at the wage adjusted for commuting costs. And so if I look at a particular residential location, either everybody in that location works in some other place, namely the place that has the highest wages net of commuting costs for this residential location. Or if I see people working in multiple places and living in the same place, they must be exactly indifferent between working in these other places. And so they must have the same wage net of commuting costs in these other places. And so you have a lot of inequality constraints on wages net of commuting costs. And so that becomes sort of super hard to analyze in a model where you have a lot of asymmetry. You've got to carry around all of these inequality constraints. And if you have a comparative static, like cutting the wall, the city in two, you're going to have these extreme corner equilibria where everybody in one place flips to work in another part of the city. And that's not at all what you see in the data. When you look at the data, you look at people living in a particular location, you see them commuting everywhere throughout the city. It's very hard to think about that in terms of all these indifference conditions. And so we're going to try to generalize the model to sort of build in the asymmetry and then to allow for a more realistic commuting pattern that's going to be closer to what we see in the data. And it's going to make the model more well behaved when we want to kind of solve for counterfactual equilibrium. So how are we going to do that? Well, we're going to sort of take the model, build an empirically tractable version of it. So we're going to think about the city as being a large number of discrete blocks. We're now going to have all of these differences in first nature geography, differences in production fundamentals, residential fundamentals, transport connections. And so we can allow for a rich asymmetric pattern of activity within the city. What's going to keep things tractable? Well, we're going to build a lot on the discrete choice literature. We're going to think about workers as being ex ante identical, but ex post heterogeneous, in the sense that they're going to draw an idiosyncratic preference for living and working in different parts of the city. Okay, so what's the idea here? Well, there are all sorts of idiosyncratic reasons why people live in one particular place and work in another place within the city. Maybe my mother lives in this neighborhood, I want to live near my mother. Maybe my aunt owns a factory in this other neighborhood and she offers me a job, and so I live in neighborhood 1 and I work in neighborhood 2. Obviously, any model we write down, we don't want to model all of that idiosyncratic heterogeneity, and so that's what this extreme value draw is going to capture. These idiosyncratic reasons people live and work in particular places. More substantively, what is this idiosyncratic heterogeneity going to deliver? Well, it's going to deliver a commuting gravity equation. And you can probably already see where that comes from. We know in trade models with extreme value distributions for productivity in Eaton Quarter, we get a gravity equation for trade flows. Well, in a similar way, in this model of commuting where we have extreme value idiosyncratic heterogeneity, we're going to get a gravity equation for commuting flows. And I'll show you later that that does a really good job approximating commuting flows in the data. And so that's going to be kind of helpful in terms of getting the model to match the data. And it'll also ensure the model is well behaved in terms of counterfactuals, because every location within the city is going to face an upward sloping supply function for workers. Why is it upward sloping? Well, if I want to attract more commuters, I have to pay them a higher wage. Why? Because I need to attract people with lower values for their idiosyncratic draws. Everyone who's got a super high idiosyncratic draw, regardless of the wage, they're going to choose to work in my location. If I start off in an initial equilibrium, I want to attract more people, I'm going to be attracting people with lower draws, so I need to offer a higher wage, and that's going to keep the model well behaved when we do counterfactuals. And then although I'm going to be focusing on Berlin, these kind of frameworks are very, very tractable. In the paper, we report a counterfactual for a change in the transport network. It's very easy to use these models to evaluate changes in the transport network. And I have a subsequent paper mentioned in the reading list on London's 19th century railway network in the QGE, where we use a related model, slightly more generalized model, to look at the impact of the construction of London's transport network. So what's the setup of the model? Some things are going to be familiar, some things are going to be slightly different. Now we're allowing for commuting within cities. So when we think about a city embedded with a larger economy that provides a reservation level of utility, U bar. So here we're going to be solving for general equilibrium in the city, but there's a component that's partial equilibrium in the sense that we're keeping this reservation level of utility in the wider economy constant. And so we think that's sort of reasonable for Berlin, although Berlin's a big city, we're comparing it to the whole of pre-war Germany or the whole of West Germany, we think that's a reasonable approximation. Again, the paper I mentioned with Esteban Rossi-Hansberg and Ferdinando Monte in the AER, we kind of generalized the model to endogenize that outside level of utility. It's actually not particularly hard to do, but in everything I do today, I'm just going to take it as given. Essentially, when you generalize it, it looks a lot like the model in the previous lecture. We've got this common level of utility that's endogenous, and that's going to depend on the choice of units, and it's actually very easy to handle that. So as I said, the city is going to consist of a set of discrete blocks indexed by I. We want to allow these blocks to have different supplies of housing, as we were discussing in the earlier lecture. So we're going to define something called phi I, which is going to be the density of development in block I. What does that mean? It's the ratio of floor space to land area. So some blocks may have higher values of floor space to land area because we build taller buildings in the center of the city than in the outskirts of the city. We're going to keep the trade side of the model super simple. So it's just going to be a single final good. It's costlessly traded within the city and the larger economy, and it's chosen as omni-rare. And so we'll just set the price. The price will be equal to 1 across every block where the final good is produced. Again, that's actually not super important for the properties of the model. We sort of made that assumption because it builds directly on the kind of canonical urban model that I talked about earlier. The Alonso Myth-Mills model makes the same assumption. So we kind of wanted to show you can take that canonical model and enrich it, take it to the data. But you can actually embed goods trade modeled in a very similar way to the way we covered in the previous lecture. And again, that's something we do in the paper with Esteban and Ferdinando Monte. We build in that Helpman 1998 version of goods trade between locations. We put that into a commuting model. And it's not particularly hard to do, but for the moment, we've abstracted from it. Partly because within cities, we don't have any data on trade between city blocks. It's very hard to gather data on trading goods at a very fine spatial scale. So here, markets are going to be competitive, again, related to the earlier lecture. So all agglomeration economies are going to have to be external economies of scale. What about workers within the model? Well, they're going to choose a block where to live, their residence, a block to work, their block of employment, their workplace, and they're going to choose how much of the final good to consume and how much floor space to consume to maximize their utility. How about firms? Well, they're going to have to choose where to produce a block of production and inputs of labor and commercial floor space to maximize their profits. And then in the land market, we're going to need that floor space will be allocated optimally between residential and commercial use, net of any tax wedges for zoning regulations. We'll allow a kind of a tax wedge between commercial and residential use, which might capture zoning regulations. And then, related to what we started with, productivity in every location is going to have two components. First, nature geography, production fundamentals, and second, nature geography, which is here going to be knowledge spillovers. So instead of increasing returns to scale, transport costs, and love of variety, the agglomeration forces here will take the form of technological externalities that are knowledge spillovers, which again is kind of closer to the tradition in urban economics, which follows that approach. And you might think that goods trade costs are relatively small between city blocks, whereas knowledge spillovers might decay quite fast across city blocks. And so maybe within cities, knowledge spillovers are relatively more important than goods trade which is more important between cities. And then for residential decisions, again, we'll allow for some first nature geography fundamentals, and then some second nature geography spillovers that depend on the local density of residents in surrounding areas. So again, in terms of flagging areas for further research, You know, on the one hand, this specification is attractive because we have first nature geography, second nature geography. On the other hand, it's extremely unattractive. Why is it extremely unattractive? Because these agglomeration forces are going to be modeled in a very reduced form way here. We're just going to assume that these spillovers depend upon travel time weighted employment density in production and travel time weighted residential density in residential decisions. And those are not micro-founded in any way. And so one really interesting area, as I mentioned in the first lecture, is developing micro-founded models of those and distinguishing between alternative sources of agglomeration in the data. So I have a paper using smartphone data that I mentioned earlier, where we're trying to explicitly micro-found these residential spillovers with shopping trips and non-commuting trips where people travel to consume services in different parts of the city. And that's a very active area trying to distinguish between these different forces for agglomeration. And I think all these new sources of data like Uber, Lyft, smartphones, credit card transactions are kind of opening up more scope to micro-found these assumptions. But here they're going to be a little bit of a black box, and that's the kind of most unsatisfied part of the paper in many ways. And then, as we mentioned earlier, workers also face commuting costs and traveling between where they live and where they work throughout the city. So a little more detail on the consumption side of the model. So some things are going to be familiar, as we said from the previous lecture, something slightly different. So we're going to think about the utility of a worker omega who lives in block I and works in block J. So again, first subscript is going to be where you live. Second subscript is going to be where you work. So what does her utility depend on? Well, it depends on how much of the final goods she consumes and how much residential floor space she consumes with the Cobb-Douglas functional form again. And in the paper, we provide some evidence with the property transactions data as well that the Cobb-Douglas functional form is not too bad an approximation for Berlin, at least in the modern data where we have property transactions. And then her utility is also going to depend upon residential amenities, capital B. So I mentioned this in the previous lecture. We're going to allow now for a Higgs neutral shifter in utility. Some places may be nicer places to live, just because if you live near a lake in the outskirts of Berlin, it's just very pleasant to be able to go swimming or be able to go boating in that lake at the weekend. And then the worker is going to face commuting costs in traveling between where she lives in I and where she works in J. We're going to assume they take an iceberg form. You can either think about them in terms of utility, which is the sort of way I'm going to interpret them during the lecture. So if you commute a longer distance, that reduces your utility. It's boring sitting on the train and you can read, or you can read for fun or for work, but it reduces your productivity, or there's disutility from that travel journey. Because you'll see in a second, the indirect utility function is actually linear in the wage. You could also think about these commuting costs as reducing your productivity, either because you have less time to spend at work, or because you get, I don't know, you lose energy when you're on the train, and so you're less productive when you get to work. And then finally, we're going to allow for this idiosyncratic draw, which is the only thing specific to the individual worker omega. And so the way we set the model up, each worker omega gets a whole matrix of draws for her preference for living in I and working in J. Okay, so a whole matrix of bilateral draws for each possible place of work and residence within the city. And we're going to assume that those idiosyncratic draws come from this extreme value distribution down here, which I know you're all going to be familiar with from Heat and Quantum in international trade. It's a Frechet extreme value distribution. There's going to be a parameter epsilon that's going to determine the dispersion of these idiosyncratic draws. So the higher the value epsilon, the less dispersed are those draws. And then in addition, we're going to have some scale parameters, T and E, which determine the mean of the distribution of these draws by residence and by workplace. So what does that capture? Well, it captures that some residential origins may be more attractive on average for workers, perhaps again because they have better amenities. And then some workplaces may be more attractive for workers, perhaps because they have more non-traded services or it's more attractive places to work. And then later on, when I take the model to the data, I'm going to show there's a whole bunch of isomorphisms in the model. So it's going to turn out that this Frechet scale parameter that controls the average idiosyncratic draw for each resonance, T, is going to basically be isomorphic to B. And so I can, I could set, without loss of generality, I could set T to 1 everywhere and just use B to capture the differences in amenities. Okay. And then here we've got the corresponding indirect utility function as we were discussing, where I've used the fact that the final good is chosen as non-rare. And And so the price is equal to 1, and so that term has disappeared. And so indirect utility just depends upon wages, net of the cost of residential floor space, residential amenities, commuting costs, and idiosyncratic draw. And so what's the advantage of making this extreme value assumption? Well, it's going to bias, as I said, distractibility in quantifying the model, taking counterfactuals, and it's also going to match this property in the data that commuting decisions follow a gravity equation. In particular, just using the properties of the extreme value distribution, the probability that a worker lives in I and works in J is going to take this standard sort of CES style form, where it depends upon characteristics of I and J, that particular bilateral commute, relative to the characteristics of all other possible bilateral commutes. And so why is this a gravity equation? Well, again, we've got some origin characteristics, the residence, such as how expensive is it to consume floor space in residence I, how nice are the amenities in residence I. So that's the resonance characteristics. We've got some characteristics of the workplace, in particular the wage. What kind of a wage can I get from working in this particular workplace? And then we've got some bilateral factors, bilateral transport costs. Okay, so that's our gravity structure. And just like in international trade in Anderson van Wiekoop, it's not only bilateral resistance that matters, bilateral commuting costs, it's also multilateral resistance. And that's or commuting costs between all other possible locations. And that's showing up in the denominator down here, where we've got the double summation over all possible residences and all possible workplaces. So classic gravity equation prediction, both bilateral and multilateral resistance. Just sort of flag another limitation of the model. So, this is going to match the feature of the data that the commuting gravity equation holds very strongly in the data. But notice that there are a couple of key limitations the way I've set the model up here. One key limitation is workers are all ex ante identical. In reality, you might think that there are high skill workers, low skill workers, workers are ex ante heterogeneous, some have a college degree, others don't. Partly we're influenced by the data. It was really hard to get the data from pre-war Berlin. The only thing we can get is total employment. So it's not really, as far as we could find, it's possible to disaggregate the data. So again, we built the model based on what data we had access to. But there's a super interesting extension there, thinking about multiple types of workers. And so Nick Stevenidis' job market paper. So Nick is at Berkeley. His job market paper on the Bogota rapid transit system develops a sort of a version of an urban model where you have multiple types of ex-ante workers. And then within each type, it looks exactly like the model here, but you just got different types. And so if those types have different shape parameters, they have different dispersions of idiosyncratic preferences, they'll react in different ways to changes in travel time. And workers will sort of different types will sort endogenously within the city as a result. Another dimension in which it's super limiting is we don't have any industry breakdown. We only have total employment, total number of people employed in each location. Again, data limitations. It's really hard to get total employment that far back in time. And so we're just going to try to argue that although this model is stylized, even so, we can go quite a long way towards what happened in the data when the city was divided and reunified. But obviously, again, an interesting extension is having multiple industries and different types of workers may be used more in one industry rather than another. And then as you shock the city, industry composition will also change endogenously. So again, just sort of flag, these are all kind of super interesting areas for extensions and further work. Yeah, question.
I was thinking that it's probably possible to get very low quality data on location composition by neighborhood from before the war. And I was thinking about like your view of adding low quality data of this sort, like number of bookstores, stuff like that.
Right.
Is that a benefit or more nuisance?
Yeah. Yeah, it's a great question. So how did we get the pre-war data? So it's kind of remarkable. The pre-war German censuses, they actually reported for every street in Berlin the number of people that lived there. And so we have this for sort of tens of thousands of streets. And so we digitized the data by street, and then we add up the streets within each of our 15,000 city blocks. And so we accurately measure population by residence for each of those 15,000 city blocks. As far as I know, the data by street were not disaggregated by type of worker. In fact, no, I know they weren't. And the microdata for the census was destroyed during the war. You can get for the Berserker of Berlin, I think if I remember correctly, I probably going to get this wrong because I'm thinking of London now. I think around 23 Berserker in Berlin. There you could get by residents at the Berserker level at those aggregate districts, but that's a lot of aggregation relative to the city blocks. And so we were really motivated by explaining things at a fine spatial scale. And so you'll see economic activity changes at a very fine spatial scale. And so I would be nervous doing too much imputation. Already for workplace employment before the war, we have to do a bit of imputation because employment by workplace is only reported at the Berserker level. And so how do we go from the Berserker to the city blocks? We actually digitized a register of all companies in Berlin for the early 1930s that reports each company, its address in a particular street within Berlin. And so then at the street level, we know the number of companies. And so we apportion the Berserker employment across streets based on the number of companies and then construct the block level data. So we are already doing some apportionment, and we validate that by showing that in the 1980s, where we actually have the employment data and the number of businesses by block, we show there's a very close relationship between employment and the number of businesses. So we tried to validate the imputation, but we were kind of nervous doing too much of that because we wanted to try to accurately measure as well as we could. But if you're willing to do things on the resonance side, potentially you could do more imputation there if you want. Yeah, question.
How much exactly is much residential choice?
Yep.
Then in the sense of like matching with the house.
Yep.
Maybe if I get into the neighborhood, it's easier to say, well, I look in the area and something, but I can get in the block.
Yep, so good question. So you might worry that our data are ready to aggregated, but I'll show you that in the data we do see big changes across blocks, and these things are very localized at the block level. But there's still enough variation, and so there's enough for us to identify the parameters of the model. Of course, there could be some reduction in signal to noise ratio from the aggregation, and already if you think about 15,000 blocks, when we're solving for commuting market equilibrium, we're solving we've got a matrix that's 15,000 by 15,000, so many millions of elements. And so when we actually structurally estimated the model, we had to do that on a supercomputer in Berlin. And so at the time, with the computing power we had, I don't think we could have gone down below the block level. And so, yeah. So you might think it's too disaggregated, but I'll show you the estimates of spillovers we get are really localized. So you'll see that I think there's actually a big gain from going from the Berserker level, which up to about 23 to 15,000 blocks. So I'll try to convince you that, yeah, that's that. So we've got this very tractable formulation of commuting decisions, and that's the probability someone commutes from residence I to workplace J. And then obviously, if you want to know the total number of people that live in each residence I, we can just sum up those bilateral commuting probabilities across workplaces. And similarly, if you want to know the total number of people that work in block J, we can just sum those probabilities across residences. Okay. And then the model also gives us a commuting probability that's going to be super useful taking the model for the data, and that's going to be a conditional commuting probability. So what is that? I can also compute what is the probability that you commute from residence I to workplace J conditional on living in residence I. Okay, so that's just this probability divided by the probability you live in residence I. That's going to be a very useful probability to work with. You'll see in a second because of the commuting market clearing condition of the model. Once I divide by the probability you live in I, it's also going to have the property that any residential characteristic is going to drop out. Why? Because this is just the scalar in the denominator. It's a double summation, so it's just a constant. And then a residence characteristic such as amenities or the price of residential floor space, it doesn't vary across workplaces, conditional on just looking at one individual residence. And so when I divide this unconditional probability for commuting between residence I and workplace J by the probability you reside in I, all the residence characteristics cancel, and I just get this conditional commuting probability down here, where the number of people commuting from I to one individual workplace J just depends on the wage, net of commuting costs, and then this average parameter that determines on average how attractive is workplace J. And then that's compared to all other workplaces that you could travel to from residence I. And so the only thing that matters here are the workplace characteristics and the commuting costs, because I'm conditioning on living in an individual residence. I'm differencing out any characteristic of that residence. Why is that a useful thing to do? Well, it turns out to be very useful for writing down the commuting market clearing condition of the model and for doing the structural estimation using our observed data. So in particular, commuter market clearing in the model is going to require that the number of people working in block J has to equal the number of residents commuting to that block in equilibrium. So summing across all residences within the city, the number of people that live in each residence times the probability that they commute to J conditional on living in residence I. And so we can use that conditional commuting probability to write the commuter market clearing condition. And so you'll see here that if we assume that the shape parameter for each workplace, EJ, is equal to 1, that there's no variation in those average workplace parameters, that's going to cancel out. And then the only thing that determines these bilateral commuting probabilities is the wage in the workplace and bilateral commuting times. And so the idea between how we take the model to the data is that what we see in the data is this employment by workplace, the total number of people who work in particular block J, and the total number of people who live in a particular block I. And we don't actually see, before the war, we don't see the bilateral commuting probabilities at the block level. But because we see employment by residence and employment by workplace, we can make assumptions about bilateral commuting costs. We parameterize them as a function of bilateral travel time, where kappa is a parameter to be estimated. And then I see travel times, I see employment by residence, employment by workplace. I now have a system of equations where the only thing that's unobserved is the wage in each workplace location. So if I see travel times, employment by residence, employment by workplace, I can just solve that system of equations for a unique wage vector at which employment in each location is equal to the measure of people choosing to commute to that location. And it's easy to see that that system has a unique solution conditional on the observed data. So from my observed residence and employment data, I can get wages, which I don't see. And that's going to be really crucial for kind of quantifying the model. We leverage that heavy in the structural estimation. Cool. Great. So that's sort of the commuter market clearing condition. And now I want to work towards thinking about general equilibrium in the city as a whole. And there are going to be two blocks of the general equilibrium I need to solve. So one of them is the consumer equilibrium. Where do workers choose to live? And then another block is going to be firms' production decision. What's firms' optimal equilibrium production decisions? So another very nice feature of the extreme value distribution is I can also compute in closed form what's the expected utility of living in the city. So I'm just integrating across the extreme value distribution, across all possible places of residence and workplace within the city. And again, using the Frechet math, which you're all familiar with from Eaton Quantum, we get this nice closed form solution. It looks a lot like the price index in Eaton Quantum. We've got a double summation because we're summing across residences and workplaces. It's a key difference. And then we've just got the average, well, it's going to depend on this expected utility. It's going to depend upon wages in all workplaces, amenities in all residences, the price of residential floor space in all residences, bilateral commuting costs for all possible pairs, and then again, those parameters that determine the average draw. And you probably remember from Eaton Quantum in the trade literature, again, Frechet has this property that the expected distribution of prices conditional on sourcing a good from a country is the same across all possible source countries. And that's a feature of the Frechet distribution. In this commuting model, there's going to be a related property. What's that related property? Expected utility conditional on choosing a particular pair, IJ, is equal to the expected utility of choosing any pair within the city as a whole. Okay. And so that's just the analogy of the Eaton Quantum result in the commuting model. What's the intuition for that? The very first time you hear it, it sounds deeply puzzling, right? Because if you think about this for a second, some pairs within the city are going to offer much higher wages. If you work in the central business district, the wage there is going to be much higher. Some residential neighborhoods will have either much more attractive amenities than others or have cheaper housing than others. So some pairs will be much better in terms of the economic fundamentals than others. And yet the expected utility conditional on choosing that pair is the same across all possible pairs. What drives that? Well, it's the idiosyncratic heterogeneity. If a pair has really good economic fundamentals, offers a high wage, low price of housing, it's going to attract workers with lower values of their idiosyncratic draw, choose that as their preferred location within the city. And so that composition effect with the Frechet functional form exactly offsets the difference in fundamentals. And so expected utility conditional on choosing each pair turns out to be the same across all pairs. And so that's going to be a nice property of the model because in equilibrium, the reservation utility in the wider economy is going to equal that expected utility of living in the city, which is going to be equal to the expected utility of choosing any pair. And so if people are indifferent, in equilibrium, expected utility of workers is not going to change in the city. It's going to be equal to that outside reservation level of utility. That's sometimes called an open city model in the literature because there's population mobility with the wider economy that offers that constant reservation level of utility. People sometimes also solve the model of what's called the closed city equilibrium. So that's the case where you assume that the city has a fixed population, in which case expected utility in the city can change if you divide the city in two or you build a new transport network. We're going to work with the open city version of the model because, as we were discussing earlier, people were fleeing West Berlin, traveling to West Germany. So there was a population mobility between West Berlin and West Germany, and we want to allow for that in the model. And indeed, the population of West Berlin declines a lot following the construction of the Berlin Wall. So I've got this expected utility result here. Why is that a useful result? Well, if I go back to my expression for the probability that people choose to commute between a pair, or the probability they choose a residence, so summing across all workplaces, this denominator here is just the power function of expected utility. It's a scalar, as I mentioned earlier. It's just the power function of that expression for expected utility. So I can start with these residence choice probabilities. I can eliminate the denominator. It's just the scalar. And I can rewrite those residential choice probabilities in the following form. It's the measure of people that choose to live in residence I divided by the total measure of people who choose to live in the city. That's the residential probability, which was on the left-hand side before. I just rearranged the equation to take it over to the right-hand side. Then I'm going to have expected utility. That's capturing the denominator from that residential choice probability. And then in the numerator, I'm going to have the price of residential floor space, residential amenities, that average parameter determining on average how attractive it is to live in a place. And then I'm going to have a term here, which is the sum across workplaces in my residential choice probability. And what does that summarize? It summarizes commuting market access. And so we get an expression that has a very, very intuitive economic interpretation of the model for consumers' choices to live in a residential neighborhood. If I see a lot of people living in a residential neighborhood, that has to mean one of three things in the model, or some combination of those three things. What are those three things? Well, either that place where I have a lot of people living has a low price of residential floor space. So the high value of the choice probability is offset with a low price of residential floor space. It's a cheap place to live, and that's why a lot of people want to live there. That's one possibility. Or if a lot of people are living there, it must have high amenities. So it's a really attractive place to live. So no matter what the prices are, everyone wants to be there for any given price. Or the third possibility, it offers good access to employment opportunities. It has high commuting market access. And you see this commuting market access is just the CS function of wages net of commuting costs. And then again, there's this term if I want to allow the average draw to be different for each workplace. Okay, so I get a very intuitive economic interpretation. Variation in the number of people living in each block throughout the city is explained either by first nature geography or second nature geography. And first nature geography is going to enter through residential amenities. Second nature geography will also affect amenities in a second. Second nature geography, access to other places, is also going to operate through commuting market access. Okay, so the model has got both first and second nature geography determining these residential choice probabilities. And the number of people living anywhere, it depends on prices, amenities, and access to employment opportunities. Okay, and then what's nice about that result is, again, the model is going to be able to explain the observed data that we see in initial equilibrium, because I see in the data the number of people that live in each block. That was what I called residence employment. I see land prices, and we just saw earlier that we could solve for wages in the model. So if I set E equal to 1 everywhere, I basically observe everything on the right-hand side of this equation. And so from the model, I can back out the implied amenities that exactly rationalize the data in an initial equilibrium up to a choice of units, up to the scalar here for expected utility. And then the very final thing we do in the model is we allow for these amenities, as we said earlier, to have these first nature components. So capital B overall amenities has a first nature component, which is residential fundamentals. So green parks and scenic views. And then it also depends upon agglomeration economies, the travel time weighted sum of residential densities throughout the city. And again, if I see the observed data, I can determine overall residential amenities. And if I know the model's parameters, I can also split up overall amenities into the residential fundamentals and these residential spillovers, because I see residence density, I see residence and land area throughout the city. K is just geographical land area, and I observe travel time. So if I know the parameters, I can split out overall amenities into the fundamentals and into the agglomeration forces. Something similar is going to be true on the production side of the model. So we've got our single final good produced under conditions of perfect competition, constant return to scale, and zero trade costs, as we said. So output of the good in block J depends upon input of floor space for commercial use. So that's the total supply of floor space L, and then the fraction of it that's allocated to commercial use. So theta is a fraction in between 0 and 1. So some blocks may be completely specialized in production. They have no residence in the data, but they have positive employment by workplace. Other blocks may have theta of 0. They have only residence, but no employment by workplace. And then output will also depend upon the number of workers I employ and the productivity in block J. And then again, I'm going to split out my productivity into production fundamentals, little a, so first nature geography, and then the travel time weighted sum of employment density, agglomeration forces. Yeah. Yes, absolutely. Yes, there is. I defined here, as we were discussing a second ago, or is it right here? I defined this notion of commuting market access here for residents, which is your access to employment opportunities. You can also think about a market access for firms, which is that access to commuters, so which is the exact mirror image of this on the workplace side. And so if you're interested in looking at that further, I've got a paper called Suburbanization in the USA from 1970 to 2000, where I kind of look at that in a lot of detail. Nick Sivanides also uses that distinction. So this is sort of commuting market access for workers, so as residents, and then commuting market access for firms as employers of people. And the model again has those two notions of commuting market access. And if commuting costs are symmetric, you can again show that there has to be a relationship between them. So yeah, you're exactly right. There's a nice analogy there with the market access and goods markets. Yeah.
To calculate on your data the sum of commuting costs incurred by consumers, am I correct if you get a lower bound on true value?
So you're interested in the incidence of commuting costs between workers and firms? Is that
No, in the total commuting costs in the economy. So my thought was that you know how many people live somewhere, work somewhere. You don't know how many people commute from A to B. So when you assume some optimality of allocation between if I work here, then I live here, and then you get a lower bound on the actual time spent on the road.
Okay, great question. So you're absolutely right that in the data, we only see total workplace employment, total residence employment. We solve for the wage vector that exactly solves this equation. The way we've set the model up, in this equation, there's actually no aggregate uncertainty. So there's no aggregate error term because we've integrated out all the idiosyncratic heterogeneity. So if the model is correctly specified, this will give us, once we've solved for wages from the system, we can immediately back out the full matrix of bilateral commuting flows. And so if the model is specified correctly, we'll get exactly the true matrix of commuting flows. So in practice, as hinted in your question, the model may be misspecified and there might be an error term in this equation. So we're assuming that it holds deterministically. There is no error term when we set up the model. And if that's the case, there would be some model misspecification, and I have to think carefully about what that would do to the expected value of commuting costs. I think if the model is correctly specified, we're going to have the true value of commuting costs, because from this, once I get this wage, I can back out the implied probabilities, so I can work out exactly how much iceberg is incurred on every possible bilateral pair. We will do an over-identification check where we compare the model's predictions for commuting, bilateral commuting flows with some limited data that we have for one of the years. And it won't be perfect, but it'll do a reasonably good job, I'll try to argue. And so we can maybe talk about that a little bit later as to, I have to think a bit more carefully about the exact direction of the bias. You're right that there is selection, and so your intuition may well be correct, but I want to think about that a little bit more. Cool. So, and then, thinking a little bit more about producer equilibrium, I can also write the production technology in dual form. In fact, in equilibrium, I know, because it's perfect competition, I know that the price of the good in every location where it's produced, which is on rare, freely traded, so the price is 1, has to equal unit cost. And so I can just set a price of 1 equal to unit costs. And because I've got a Cobb-Douglas functional form, I'm going to get this very simple zero profit condition in the model that says in every location with positive production, the following relationship has to hold between the price of commercial floor space, wages, and productivity. And so just as we saw for residential choices, the model is going to have this invertibility property. In the data, I see the price of floor space, so I observe Q. I can solve for wages from the observed workplace employment and residence employment. And so I have an equation for every location in terms of those 2 observed variables and a single unknown in each location of productivity. And so I can back out the implied productivity in order for this to be an equilibrium where firms are making 0 profits across every location with positive production. So from the observed data, I can uniquely pin down overall productivity. And again, with my functional form assumption, if I know the parameters of the model, I can split out overall productivity, capital A, into first nature geography, production fundamentals, and second nature geography, the agglomeration forces. Okay. And this is going to play a key role in how we structurally estimate the model. This ability to solve for these first nature production fundamentals and first nature residential fundamentals that we saw a second ago. Okay, so I'm getting a little short on time, so let me make sure, I'll just do the final component of the model. Final component that has to hold in equilibrium is the land market has to clear. So demand for floor space has to equal the supply of floor space. So this is total residential demand for floor space on the right-hand side, just comes from workers' utility function. And then this is the supply of residential floor space, the overall supply times the fraction that's allocated residentially. And then similarly from firms, profit maximization and 0 profits, we have demand for residential floor space from the first order condition on the right-hand side here. And we have supply of commercial floor space on the left-hand side, overall supply times fraction used commercially. And then as we discussed in the first lecture, so we're going to kind of microfound the supply of floor space as being a competitive construction sector that uses land and capital. So land is an exogenous supply. The area of the block we see in the data. Capital is perfectly mobile across locations. And so MI is the quantity of capital I use in a location weighted by its Cobb-Douglas exponent. And so I can write the supply of floor space as just the land area weighted by its Cobb-Douglas exponent times this term phi I, which is going to summarize the density of development. And so in the data, that's going to be the ratio of floor space to land area. And then if I just add these 2 demands for residential and commercial floor space, they have to equal overall supply of floor space. And so that gives me my overall market clearing condition. Okay, so how does this model help us think about the impact of the division of Berlin and its subsequent reunification? Well, first I'm going to talk through the qualitative predictions of the model, and then we'll try to just show you the data and convince you that what we see in the data bears out the model's predictions qualitatively, and then we'll do the full structural estimation and show you that for plausible agglomeration parameters, the model can actually replicate what we see in the data. So we're in this pre-war equilibrium. We're going to think about division within the model as we cut the city in half and we end all goods trade and commuting flows across the boundaries between West Berlin and East Berlin. When we look at the impact in the data, we're going to focus on West Berlin because it remained a market economy. We might expect the predictions of the model to apply. Whereas in East Berlin, there were housing prices, but they bore very little resemblance to allocations because allocations are centrally planned. So what does the model say is the effect of cutting the city in half? Well, firms in West Berlin cease to benefit from production externalities from employment centers in East Berlin. That reduces their productivity and hence lowers land prices and employment. That's the sort of first channel. Secondly, firms in West Berlin lose access to flows of commuters from residential concentrations in East Berlin. So they have a lower supply of commuters, that increases the wage they have to pay to attract a given number of workers because of that upward sloping supply function. And so that reduces land prices and employment for any given productivity in the location. So that's that kind of second channel. Third and fourth channels, residents in West Berlin lose access to employment opportunities in East Berlin. So that reduces their expected income because they've no longer got the option of commuting to jobs in East Berlin, for which they may have a high idiosyncratic draw. So that reduces their expected income. And again, that's going to reduce land prices and reduce residents as people move out of West Berlin to the wider economy. And the residents in West Berlin are also going to cease to benefit from residential externalities from East Berlin. They don't get the spillovers on residential decisions from being near people in East Berlin because there's now no interaction across the boundary of the Berlin Wall. And so that's our final and fourth channel there. And if we assume that commuting costs increase with travel time and the residential externalities decay with travel time, and indeed that's what we're going to estimate in the data later, then all of these effects are going to be stronger in the parts of West Berlin that were close to concentrations of residents or employment opportunities in East Berlin, because they lose access to these nearby concentrations of either employment or residents just east of the Berlin Wall. So what restores equilibrium? Well, in the new equilibrium, firms are going to make zero profits in each location with positive production. Workers are going to be indifferent across all locations with positive residents. And the thing that adjusts is the number of people living in each block in Berlin, the number of people working in each block in West Berlin, and equilibrium land prices. They all adjust until we get back to a zero profit equilibrium of production, and utility is equal to the reservation level of utility in the wider West German economy. So what do we see in the data? Is there any evidence that those predictions are borne out? So as we said, we've got our three sources of data: land prices, workplace employment, residence employment, and travel time. We've got them for Greater Berlin in 36 and 2006, and for West Berlin in 1986. So I knew I'd get the number of districts wrong. There are 20 in Greater Berlin. And we've got around 15,000 blocks in Berlin as a whole, around 9,000 in West Berlin. Land prices, one of the nice features of this application is Germany is one of the few countries that actually records what are land prices. So in particular, there's actually a land valuation committee that for every block reports the official land value of a representative undeveloped property. So it's the price per square meter of undeveloped land in this part of the city. And it's meant to be the fair market value of this undeveloped property. And if the land's already developed, we still value what the undeveloped value would be. How does the committee come up with these prices? Well, they base them on market transactions. And we kind of validate the official assessed values we have in 2006 by comparing them to property transactions. And there's a very close relationship between the property transactions and the market valuations. We were lucky we found a book at the street level that reports these for every street in Greater Berlin before the war. And so we digitized all those street level data and again, aggregated up to the block level. And then we used a lot of other geographic information systems data as well that I'll highlight as we go through. So what did the distribution of land prices in Berlin look like before the war? So this is Greater Berlin in 1936. Land prices here are normalized to have a mean of 1 across all of the blocks. And I'm going to do that in every graph that follows. So the height of the peaks will be comparable across the figures. And as you can see here, the land price gradient is approximately monocentric with a land price peak just east of what became the Berlin Wall in the district Mitte that we flagged earlier. And then around that land price peak, there's sort of a sequence of concentric rings of progressively lower land values. This gap here, which you can just about see, is what anyone who's been to Berlin is the Tiergarten Park just west of the pre-war central business district. And this peak here is part of that concentric ring around the pre-war central business district. It's an area called the Kudamm or the Kurfürstendamm, which is a shopping district in part of West Berlin. And as you can see, although it's approximately monocentric, there's still quite a rich pattern of variation in land price that we see across different parts of the city. So which parts of this gradient in 36 were to become in the future parts of West Berlin and which parts were east of the Berlin Wall? So now I'll show you the same gradient again in 1936, but just for the parts of the city that became part of the future West Berlin. And so as you can see here, there were two parts of that land price gradient that ended up west of the Berlin Wall. There's this one peak, which is just west of the pre-war central business district in Mitte, which is the area around what's called the Anhalter Bahnhof station, which is a sort of major station in Berlin, and was an area of retail and office development before the war. And this again is the area I mentioned earlier, the Kudamm, further in the west of West Berlin. Now we're going to roll forward 50 years and look at that land price gradient in 1986. And you can see one of those areas of high land prices just west of the pre-war CBD is entirely eliminated, and the Kudamm becomes the West Berlin Central Business District. And so this is consistent with what the model predicted, because this area here loses access to nearby concentrations of employment and residence. So there's a disproportionate impact on land values. So qualitatively, we see what we might expect from the model, that high peak of land values is eliminated by division. One of the worries you might have is, well, perhaps that's just capturing an amenity effect of the wall. Maybe land prices fall there because you're just next to the wall and it's sort of ugly looking at the wall. But we find very little evidence of any impact of the wall on other segments of land prices or residence or employment. It's only these parts of the city that were just west of the pre-war central business district where we see these large impacts on land values. Yeah, question?
Is there a change, a large change in the variance of prices, and is that the recurring model?
Yeah, so that's also a feature that you see as you're highlighting that the peak here is lower and there's less dispersion. That's also something that comes out of the model. This is a lot of heterogeneity at the block level in these residential externalities. And so when we look at the estimated model, that's also a feature of the model-based predictions that you see, that when you cut the city in two, you get this sort of compression of the overall distribution. Yep.
But could you have different degrees of tension along the wall? I can imagine probably more political tension in the center.
Yeah, so good question. So we tried to look at that. We looked whether there were any, if we exclude this area just west of the CBD, we looked whether we found different effects for, say, the British sector and the American sector along the edge of the wall, and we didn't find any systematic difference between those. I mean, I think if you thought the Soviets were going to come into West Berlin, I think, the expectation was they would just bulldoze their way into the entire of the city, and there wouldn't be a localized incursion. So I don't think that's the case. And the leading checkpoint for the American sector is not exactly here, it's further along the Berlin Wall. So I don't think that's the case. But yeah, it's a great question. And then rolling forward to 2006, how does the land price gradient look? Well, we see these sort of two key things. We see this resurgence of a peak of land prices in the central business district. And we also start to see a resurgence in land prices in this area just west of the central business district in the part of West Berlin. And you see that if we just focus again on the areas that were part of West Berlin before reunification, again, you see this reemergence of this peak of higher land values. So then what we do in the paper, I'm kind of getting short on time, but there's a whole kind of reduced form section of the paper where we essentially estimate difference in difference regressions. And we parameterize distance to the central business district by a sequence of 500-meter grid cells. And we estimate treatment effects on each of those grid cells for the change in the price of land, or the change in residence employment, and the change in workplace employment. And we show that we find this qualitatively what the model predicts. We see land prices falling close to the pre-war CBD, we see residence falling, workplace employment falling, and all of these effects are really localized for the areas just west of the pre-war CBD. We don't see them on other parts of the Berlin Wall. So we include similar indicator variables for distance to the inner boundary between East and West Berlin, the outer boundary between West Berlin and East Germany, and so on. We show these effects are not explained by, say, proximity to parks, proximity to schools, so they include a lot of hedonic characteristics, letting the coefficients on them change over time. And again, we continue to find these effects. The other thing we do is check for pre-trends before division reunification. So as well as those reduced form regressions, this is the long difference for the change in prices of floor space between 36 and 86. Plotted against distance to the pre-war CBD, you see this extremely nonlinear decline in the price of floor space. That's the long difference for unification. Again, the nonlinearity increasing, smaller in magnitude, in part because there's a shorter length of time since reunification in our data. Then we show that most of the decline during division actually occurs in the first period of division. So the economy reacts pretty quickly to this severing of links with the adoption of central planning in East Berlin in 1949. And if we look at the period 1966 to 86, the gradient is pretty flat. And so that suggests that this resurgence post-reunification is not capturing a pre-trend immediately before reunification. And similarly, if we look before the war, between 1928 and 1936, this decline following division is not capturing a pre-trend before division in the area before the Second World War, because the gradient's very flat for that pre-period before the Second World War. So qualitatively, it looks like the model is capturing the patterns we see in the data, but what we'd like to do is structurally estimate the model. And so we do that in two ways. The first way we estimate it is we estimate just the commuting parameters in the model. And the reason that's a useful thing to do is it enables us to quantify the impact of division on productivity and amenities. So the model has this sort of recursive property that we can recover overall productivity and overall amenities without knowing the agglomeration parameters, because we can recover the overall values irrespective of how overall productivity or overall amenities is broken down between fundamentals and externalities. So there's a kind of sequential or recursive structure of the model. And so just knowing the commuting parameters, we can recover overall amenities and productivity. And that allows us to check whether the model without agglomeration forces can match the data, because if there are no agglomeration forces, overall productivity and overall amenities are only driven by first nature geography, by these exogenous fundamentals. And we show you the model with exogenous fundamentals just cannot match the data. In contrast, when we estimate the agglomeration forces later, we're going to find that the model with those agglomeration forces can actually approximate what we see in the data. So how do we estimate the commuting parameters? Well, it's kind of challenging, but we have some data on commuting at the aggregate level of the districts of Berlin for 2006. And so what we do is we use those commuting data where we have them for the post-reunification period, and we estimate the model's gravity equation for this unconditional commuting probability. So we include resonance fixed effects, workplace fixed effects, and bilateral travel times, and we estimate the coefficient on those bilateral travel times. We've got exponential commuting costs, and so we've got a semi-elasticity here. Nu is actually a composite parameter, like in the trade literature. The response of trade to distance is a composite of the elasticity of trade cost to distance and the elasticity of trade to trade costs. In a similar way here, the elasticity of commuting flows to travel times is a composite elasticity, elasticity of commuting flows to commuting costs, and the elasticity of commuting costs to travel time. And so kappa is the elasticity of commuting costs to travel time, and epsilon, the Frechet shape parameter, controls the responsiveness of commuting flows to commuting costs. So we can estimate that composite parameter from just running gravity equations. How well does the model's gravity equation prediction do? Well, it's not perfect, but it does a reasonably good job. So this is our estimate for this semi-elasticity. We first just take logs and estimate it OLS, pretty high R squared here, around 82% of the variation. These commuting data we have are for the berserker of Berlin. And so in actual fact, there are no zeros at that aggregate level. So when we take logs, we're including all bilateral pairs. But as a robustness test, we dropped the pairs with very few commuters, because you might be worried about granularity there. You've got very few commuters on an individual link, so there could be a lot of idiosyncratic error there. So we dropped those. You get a very similar point estimate, slightly higher R squared, as you might expect. We also, like in the trade literature, one concern about a log linear gravity equation is heteroscedasticity. And so we re-estimate the model with Poisson's pseudo-maximum likelihood and gamma pseudo-maximum likelihood. And across all these specifications, we get a pretty consistent semi-elasticity for commuting flows. And then we plot the actual data against the fit of the gravity equation in 2008, where we have our commuting data. And you see it's not perfect, but it does a reasonably good job. And then this is using the models. Once we've estimated that parameter, we solve for wages in the way I showed earlier. We generate predicted bilateral pairs for commuting flows, as someone was asking earlier, which are deterministic. And then we graph those, we aggregate them up to the district level, and we graph them against the commuting probabilities in our district level commuting survey data. And it's not perfect, but there's a very strong relationship between what the model predicts and what the data say. That commuting parameter is estimated in 2006. You might be worried, how well does that do going back to before the war or going back to division? Those are very long time periods. Fortunately, we managed to find some data on commuting back to the 30s. What we have is a guy who was actually an economist at one of the German universities in Berlin. He took a survey of a number of firms in different parts of Berlin, and he asked each worker, how long do you commute to work each day? And so we know kind of the fraction of workers that commute, say, less than 10 minutes, 20 minutes, 30 minutes, and so on. We have a cumulative distribution of workers' commuting distances. And so what we do here is compare the model's cumulative distribution to the pre-war data and to the similar data for West Berlin during division. And it's not perfect, but it looks like we're doing a reasonably good job against those cumulative distributions.
Just out of curiosity,
Yep.
Where did the purple tongue data for 2006 come from?
We got it from the statistical agency in Berlin, which tells you the transport. It gives you a shapefile of the transport network. So it gives you a line in latitude, longitude space of the pattern of the underground line, the streetcar line. So we start off with those shapes in geographic space. And then we, to solve for commuting times, we start from each block, each residence block to each workplace block. And we assume a travel speed for each of the different modes of transport based on average speeds reported by the statistical agency. And then we assume that workers solve for the least cost path, given those assumed travel times. We allow them to change between different modes of transport. And we assume, if I remember correctly, it takes 3 minutes cost when you switch between modes. So maybe like a loss of time while you're waiting for the connecting train. And so we compute all of those travel times from the observed network. And then there's a validation in the appendix. We compare what you'd find if you plug those coordinates into Google. And we show, at least for 2006, our estimates get pretty close to the reported kind of Google travel times for the public transport network. So then I promised I'd show you what happens in the model without agglomeration forces, and try to convince you that can't explain what happens in the data. So now we've got our commuting parameters. We get that composite parameter, epsilon times kappa. And then we actually solve for epsilon from some wage data we have. So we look at the dispersion of wages, which provides a moment to identify epsilon in the model. So then we can split out epsilon kappa into epsilon and kappa. And then once we've done that, we can use the result in the model that we can solve for overall productivity and overall amenities, regardless of the importance of agglomeration forces. And one first piece of evidence that a model without agglomeration forces is not going to explain the data is, once we've solved for productivity and amenities, we find very strong treatment effects for them. Following division, amenities falls a lot close to the pre-war CBD, productivity falls a lot close to the pre-war CBD. That's the first piece of evidence that a model without agglomeration forces is not consistent with the data. Second piece, factual for division inside of the model, and a counterfactual for reunification, and we solve for the new land prices, and we show that if amenities and productivity are exogenous, again, there's a unique equilibrium, so improving systems uniqueness when those are exogenous or no agglomeration forces. And the model does give us treatment effects. It does generate falls in land prices and rises in land prices following reunification in the parts of West Berlin close to the former CBD, but they're just much smaller than what we observed in the data, and statistically significantly different from what we observed in the data. And so the model without agglomeration forces is not able to match what we observe in the observed data. And then I'm getting short on time. I'll try to keep on time. The very final thing we do is we structurally estimate the full parameter vector. So that's the commuting parameters. So nu, our composite parameter, epsilon times kappa, and epsilon. Again, we use commuting moments and wage dispersion moments to pin those down. But we now estimate them as part of a simultaneous procedure, where we also estimate the relative importance of fundamentals and agglomeration forces in production, the relative importance of fundamentals and agglomeration forces in amenities, and the rates of decay of production agglomeration forces and residential agglomeration forces. How do we estimate them? Well, we use the fact, as we highlighted earlier, we can solve for these fundamentals in production and in residential decisions, for any given parameter vector. And those fundamentals are essentially structural residuals that exactly match the observed data, so the model exactly explains the observed data. So how do we estimate the parameters? Well, we use orthogonality conditions on those fundamentals. What are the orthogonality conditions? Well, we assume they're uncorrelated with distance grid cells from the pre-war central business district in West Berlin. So what's the identifying assumption? That reorientation of economic activity that we saw in West Berlin is entirely driven by the model's forces of agglomeration in production, agglomeration in residence, and commuting costs. And the changes in the fundamentals before and after division are orthogonal to distance in the pre-war CBD. So that's the kind of exclusion restriction. What do we find? Well, we find pretty strong agglomeration forces. So we find an elasticity of productivity to the travel time weighted sum of employment density of around 7%. The existing literature looking across cities gets elasticities between 3 and 7%. So we have a bit of a high, we're at the top of that range in terms of our estimates. It's pretty similar whether we just focus on the division experiment, just reunification, or we pull both. Another interesting feature, we find large elasticities of residential amenities with respect to residence density. So here there's been much less work. There's a lot of work on agglomeration and production, relatively little on the residential side. We actually find that it's stronger on the residential side than the production side. And several other recent papers, including Rebecca Diamond's job market paper, she finds very strong agglomeration forces in residential decisions as well. So sort of several papers finding that. And as I highlighted earlier, developing better micro foundations for this finding is a really interesting area of further theoretical and empirical work. The other thing we find is very high rates of exponential decay, so rho and delta of both production externalities and residential externalities with travel time. So these agglomeration forces are strong, but they're highly localized between blocks, relating to one of the earlier questions about the level of aggregation. And so to make that more interpretable, we're showing you here the effect, of going from the effect of travel time weighted employment density with a travel time of 0, so no decay, and then increasing that travel time in minutes as you move away from the employment location. And you can find that by around 30 minutes of travel time, those externalities have completely declined to 0. So, excuse me. And so what is 30 minutes of travel time? It's around I think it's around 3, if I remember correctly, 3 to 5 kilometers walking, and obviously, it's a shorter distance if you take underground the suburban railway. I think it's between sort of 500 meters and a kilometer, if I remember correctly, if you take the suburban or underground railway line. Also true for residents, but commuting costs decay much less rapidly, and that reflects the property of the data that you see people commuting pretty long distances in the data. The only way the model can rationalize that is say it's actually not that costly to commute long distances. And then the final thing we show is that once you've estimated the parameters, if you now use the model to solve for a counterfactual equilibrium, and you estimate our reduced form regressions on the model's counterfactual predictions, you get estimates for treatment effects of division very, very similar to those we estimated in the data. So the model, once you estimate and allow estimated agglomeration forces, it can quantitatively match the values we observe in the data. Of course, we use these moments for estimation, so this is sort of a within sample fit check. And in the paper, we also report some over-identification checks using moments we didn't use in the estimation of the parameters. Okay. So what is the punchline to finish on time? We tried to develop a model now looking within cities, taking account of commuting, where people can separate where they live and where they work, that can rationalize the observed data. It can allow for first nature geography, differences in fundamentals, as well as agglomeration forces. And we tried to see whether a structurally estimated version of the model can actually match the impact of this experiment that we see in the data, cutting Berlin in two by the Berlin Wall and reunifying it following the fall of the Iron Curtain. In the raw data, we see qualitatively what the model predicts in terms of reallocation of land prices, residents and workers. We find the model without agglomeration forces can't replicate what we see in the data, but once we allow for the estimated agglomeration forces, it does a relatively good job at capturing this large-scale reallocation of activity. And sorry for hitting bang on time there, but I guess we should stop there or take a couple of minutes of questions before the lunch break. Thank you very much. Any further questions? Yeah.
There is more question.
Yeah.
Whether it would consistently with a different political situation where you have consistent story on the other side of the wall. Maybe by given construction, time for apartments, location choice by party level, I don't know. But we try to see a consistent story there.
Yeah, it's a great question. So we tried to get the data. We couldn't find any data on a consistent basis. We found some patchy data on rental prices at a very aggregate level, but we couldn't get it at a very fine level. But I do have another paper on the division of Germany that I mentioned earlier, where Germany was cut in two. And we used a sort of market access model we analyzed in the previous lecture. We applied in West Germany. We find very much the model quantitatively matches what we see in the data. Then for East Germany, we can get the same data there. We can get the population of East German cities. We actually see a different pattern in the East. That whereas in the West, there's a decline in cities close to the new border, which is what the model predicts. In the East, if anything, there's an increase in population close to the new border. And so we interpret that as the East German authorities wanting to sort of build up this area close to the border and not wanting it to decline, because wanting to signal this as part of the East German state. And so we actually do see a different pattern of results there in the East where market forces are not applying. We did try to get better data in the East, but we just weren't able to find it. It's possible it exists somewhere, but our co-author in Berlin, he was, sent him running around different archives in the city. He was getting pretty fed up with us. We couldn't find anything, but I mean, it would be super interesting if any better data is discovered. I'd actually like to do something on the impact of communism. So that would be kind of very interesting. We basically couldn't find the data to do it. Well, everyone's probably really hungry. I kept us going to our lunch time. So, but yeah, it would be great to talk more over lunch. Okay, thanks. Okay, thank you.
Thank you.
Thanks. Oh, sorry, I didn't see there was a question in the chat. Workers homogeneous. Okay, hopefully we address that question. But thank you very much.